All right. Well, hopefully we won't have any trouble with the equipment here. I just moved in your house and I'm trying to set up everything. So let's see, I'm operating normally. I'm hardwired in, but today I'm going to do Wi-Fi. See how it goes. All right. So what do you have today? You have the next exam, chapters 4 through 6. Don't forget about that. If you have any questions, more than happy to cover it. We can talk about it. If not, we'll continue with the chapter we were on, which was 7. Okay. Any questions? Okay. Well, if you do, send me an email. I'll be monitoring my emails very close. Okay. All right. Well, let me share the screen. And we were getting ready to talk about Lewis dot structures. Okay, that's where I ended up here, slide 17. Let me back it up here. Okay, we had just finished talking about the Lewis dot structures for specific atoms, and it's only for the ones in the A group. Okay, because those we can predict the valence electrons, the number of valence electrons. The B group, the B elements, not so much. So here we're asked to write the Lewis dot structure for the atoms of potassium, oxygen, silicon, magnesium, and iodide. Straightforward. You look for the element, find what group it's in. That tells you how many valence electrons it has. Put a dot on it to represent the number of valence electrons, and you end up with something as follows. So that's a depiction of the valence electrons, and again, valence electrons, the outermost shell of that particular atom, the outermost shell that contains the valence electrons. Okay. All right. Now we're going to be talking about the Lewis dot structures for actual compounds. Okay. So we have a stepwise process to do this. One, we add up the total number of valence electrons that all of the atoms of a compound bring to the table of the structure, if you will. Okay, so we go find them on the periodic table, count the number of valence electrons that atom has, multiply that by the number of those specific atoms, and then we just tally up. When you are done doing that, you should always end up with a number that is divisible by 2. Okay, always. If you end up with an odd number, then there's a problem here, and then you need to check it out and verify that you did select the correct number of valence electrons. You will always be given the central atom or being told what is a central atom. Remember that there's all in the chemical compounds that we're going to work with, there is a central atom in the middle, and then all of the other atoms that are associated with that central atom are bonded to the central atom. Okay, so we can very quickly draw a line from the central atom to all of the other atoms that are bonded in the peripheral, if you will. And then that takes care of, a line represents 2 electrons. So that takes care of 2 electrons. For example, let's say we have a hypothetical compound of, what happened to the line? Second. For some reason, this isn't working. All right, so maybe I can do it this way. So if we have a hypothetical compound with, I'm using my mouse and that way we can call it X, and then we have bonded to it, call it Y. So we got maybe 3 Ys. Okay, so that's a Y, that's a Y. I'm gonna see if I can fix my pen a little better. But that particular line right there represents 2 electrons. So here we made 3 bonds of X bonded to Y, X being the central atom and the Y is bonded to that. Okay, clear this up. One more thing, can I get my writing pad working here? Bear with me for a second. So you get, you know who is the, be given who is central atom. Then, once we put all the bonds together, we got to make sure that everybody has the octet fulfilled, that there are 8 electrons around the specific atom. Okay, and some of these may be shared with another atom. So any bond between, like that example, X and Y, that bond of 2 electrons is shared with both X and Y. Okay, so they count as 2 for X and then also count as 2 for X or Y, whichever one. Okay, so we go around checking to make sure everybody's fulfilled with respect to octet, 8 electrons, except hydrogen. Hydrogen only has 2. Okay, hydrogen will never have more than 2 electrons bonded to itself. So once we do that, if for some reason we come up shy in one atom and says, okay, I don't have enough electrons, then what we start doing is we start sharing more bonds. We start with a single bond, and then we go to the neighboring atom and borrow a pair of electrons and create a double bond. If that works, we're good to go. If it's not, we're still short, one of them's still short, then we make a triple bond. So we start with a single bond to make sure the octet is fulfilled. If not, then we create double bonds because we're going to share electrons with the neighbor. And if that doesn't work, we make triple bonds, and that's maximum. Single, double, or triple bonds are created. All right. Then we're keeping track of the number of electrons that we have. Because if you add up you tally up and you come up with 10 valence electrons for this molecule, that is what you have to work with. You cannot add more or subtract. That's what each atom brings in. So you got to make those 10 work. If you end up with too many electrons or not enough electrons, what probably happened is you may have picked the wrong valence number, valence electrons to tally it up. So check your math, make sure you pick the right column for that particular atom. Okay, so bear with me for 1 second. All right, so at the central atom, we then note at the central atom how many electrons are bonded, because you will have in some scenarios where on the central atom only, that's all we're concerned about at this point, you're going to have all 4 bonds. It'll be at the maximum 4 bonds for the central atom. And that 4 bonds would be a combination of 4 singles, or 2 singles and a double, or a triple and a single, being that you end up with 8 around it. So you go back and check, make sure that they have 8 in the central atom, identify which ones are bonding, the number of bonding electrons, and then identify how many what are called lone pair. You will, on occasion, on the central atom, you have an extra pair of electrons in your inventory of electrons, valence electrons, and they can't go anyplace else. They have to go in the central atom, but they're not bonded to anything, and that's okay. Then those are called lone pair. They are not bonded and they're not shared with anything else. They just sit there on the central atom. Okay. Now we want to do that because we're going to create the general formula. Okay, the general formula of A, B, and E. Okay. Now A represents the central atom. Always going to have 1A. B represents how many atoms are bonded to the central atom, okay? You could have, B can be all the same or different, doesn't make a difference. All we want to know the total number of atoms bonded to the central atom. And then E represents the number of lone pairs on the central atom. This general formula is crucial here because that's going to help us to go to the table to help us determine the general shape of your molecule. A is by itself, always A, regardless of what it is. It could be oxygen, carbon, whatever the case may be. B, again, can be more than, could be all the same elements or different. And then we put a subscript, which it doesn't support subscript here. But let's say, for example, we have two B's, and that's AB subscript 2, okay? And then maybe we got two A's, so it's AB subscript 2E subscript 2, okay? So our general form is AB2E2. What we do with that information is we go to the periodic table, specifically, the shapes table, and we use the shapes table. Notice in the first column, you have the general formulas, A, B, E. Sometimes we have no E's, sometimes we do. The first three examples have no E's, meaning that the central atom has no lone pairs, okay? And B, again, represents any atom that's bonded to the central atom. So the example I just gave you, which was AB2E2, which would be this guy right here. You see him? Okay, because that means there's two items bonded to the central atom and it has two lone pairs. That is the three-dimensional model of the molecule you just determined with the information you're given. That is its particular molecular geometry, which has a specific name, and we call that bent. Notice the lone pair is kind of exaggerated with that little circle, and two little dots. But those two little dots, two pairs, are the lone pair on the central atom. On this right here, central atom. We don't care about what's bonded lone pairs on B's and whatever's outside, just in the central atom. Now, with that being said here, notice that the last column says the angle 109.5. Let me digress a little bit. The most common structure that we find out in nature is the AB4, meaning that we got a good example of this would be carbon and then 4 hydrogens bonded to it, okay? And it has that general formula, AB4. Remember, ABE is a general formula. It has nothing to do with the actual chemical structure, the chemical that you're working with. It is taking the valence electrons, determining how many are bonded to the central atom, how many atoms, and how many lone pairs. That's all it is. Don't confuse the two. This is not an actual chemical, ABE. It's just a general formula. So AB4 is the most common structure that's out there in nature, and three-dimensional model is shown right there. Here. Now notice that in that line right there, that represents a bond. 2 electrons that are bonded between whatever these two items are. But there's 4 of them bonded around the central atom. Now those are electrons, and so they're going to interact with the other lone pair, the other 3 pairs. So they're all interacting. So what happens is they put themselves in the configuration, because they're negative charge, where they have maximized the repulsion that they have for each other, and that is the maximal configuration that they can come up with, and we call that tetrahedron. Okay, right here, and that bond angle, and that is you can see it here, is 109.5. That's a 30 standard bond angle, and its bond angle is designating that right there, the bond angle between 2 atoms bonded to the central atom. Okay, now, when lone pairs come into the central atom, they tend to occupy a lot more space. Why is that? Because you got 2 negatively charged species there. Okay, you can see it here in this other example right there. they're going to repel each other. And so what the result is, they take up more space, the lone pair, resulting in this angle right here that we would anticipate to be 120 all the way around, but like this one up here, like this example up here, because everybody's spread out, it's maximum spread out, maximum repulsion as far as the electrons get 120, but you put a lone pair, they occupy more space, so resulting in that bond angle, instead of being 120, to be less than 120. Now, for the tetrahedral example, if we were to take one of these species, like, take this guy right here, I'm pointing to right there, maybe we'll change its color. If I take this atom and put a lone pair there, I end up with this particular structure, okay? So now I got 3 atoms bonded to the central atom, and they're lone pair. By the same reason we just talked about in the previous example right there, those lone pairs take up more space. And so they push the other electrons down, resulting in a bond angle, which is now much less than 109.5, relative to the standard 109.5. And that is because the lone pair. One effect of that is something to remember here or down the road, is that makes that molecule, its physical property becomes what we call polar, okay? Polar meaning more like water-like. We got nonpolar, excuse me. Nonpolar is like, think about like oil-like. And we know oil and water don't mix, okay? And so it makes a molecule, any molecule with a lone pair in the central atom automatically is classified as a polar species. Okay, now that's with one lone pair. And then if you have 2 lone pair, by the way, the shape with one lone pair is trigonopyramid. Okay. Now when you have, let me clear it up, I got a lot of mess going on here. When you have 2 lone pair, that bond angle right there is bent even more, okay? Because now you got 4 electrons, lone pair, 2 lone pairs, so a total 4 electrons that require a lot of space. So that bond angle is much less than 109.5, and it has a specific name for that particular geometry, and we call that bent. A classic example of this configuration or this geometry is water. Water has a bent molecular geometry. Okay, so with the general formula that we determine by the valence electrons, we bring to this table, and then from that general formula are able to determine for that molecule its molecular geometry, its name for its shape, and that bond angle associated with that particular geometry. Okay, so the shapes table is very important here. Okay, so let's go back and maybe we do some actual examples. Bear with me for 1 second. I may disconnect you for a second, bear with me. Okay. But let's do an example here. So let's do water. Okay, so H2O, identify how many atoms you have of how many different atoms you have. So H2O, the subscript 2 tells us we have 2 hydrogens and 1 oxygen. So from that information, we go to the periodic table, and that tells you how many valence electrons each atom has. We know that hydrogen is in group 1 and therefore has 1 valence electron, and there are 2 of them, okay? And we know that oxygen is in group 6, which tells you you have 6 valence electrons. So we have a total of 8 valence electrons, okay? Now, what I like to do is once I calculate the total number of valence electrons, and the small number is not too bad, you can deal with the small number, but occasionally you could end up with like 32 valence electrons. So you should always get a number that is divisible by 2. And so here, 8 divided by 2 obviously tells me that I have 4 pair. And I use that 4 pair because I can just make a line. A line represents a pair. So I can very quickly, instead of doing dots, dot, 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 I can very quickly just draw a line. Now, excuse me. You're welcome to do the dots, that's fine. But like I said, you can end up with 32 dots in your structure. That's a lot of dots, and you can end up losing dots. So I prefer just to make a line to represent a pair. So in this example, tells me I have 4 pair. So oxygen is a central atom. And normally my drawing pen works here, but I can't do it, so I'm going to try to do it this way. So I can very quickly draw H and then draw a line, which this hyphen represents a line, and then oxygen, and then another line, which represents the other bond to oxygen, okay? So each line there tells me now I have 4 minus 2, so that is equal to what I got left over, 2 pair of valence electrons to work with, okay? Now, I can't put them on the hydrogens because hydrogens, remember, they have the duet rule. They're happy. And so the only place I can put those 2 pair of remaining electrons is on the central atom, in this case, oxygen. Because right now, oxygen has 4 valence electrons or 4 electrons around it. So it has not fulfilled the octet. But putting that 2 pair on the central atom, guess what? Now you have 8 electrons around the central atom. Let's draw the structure here. And so you see that we got the 2 lines that represent the lines are between hydrogen and oxygen, that's a pair. And we have the 2 lone pair on the central atom, which is oxygen. We still have a total of 4 pairs. 2 of them are being shared with the oxygen. The oxygen and hydrogen are sharing it. And 2 of them are lone pair. So in this scenario, our general formula, we would write A, always A, okay? And we got B, but we do a subscript, so I can't do subscript, so that's subscript B because there's 2 hydrogens here. And there are 2 lone pair, which are represented by the letter E, and there are 2 lone pairs, so subscript 2. So our general formula here is A, B2, E2, okay? With that information now, you go to the shapes table and look for AB2, and it's right here, AB2E2. So that is the general formula that we just determined. There's a picture of the geometry, and there is the name for that particular geometry. And as I mentioned, when there is 1 pair of electrons in the central atom is polar. When you got 2 of them in the central atom, it's very, very polar. So water is very, very polar. It's a good example because of those lone pairs on 2 of them on the central atom. Okay, so any questions at this point? All right, so with that, let us figure out what we need, how we're gonna do this. All right, I'm gonna do this a different way. Bear with me for 1 second. I'm going to try something on my computer so I can get my pen to work again. Okay. So I might lose sight of me for a bit. All right, well, we'll do it this way. All right, so what we do here is we start off with the formula. We're given the formula HCN. What it is at this point, 9 form here. I'll tell you what they are as we progress. But you notice that the carbon is underscored. Okay. So that tells you that carbon is central atom, which means that the nitrogen and the hydrogen are bonded to the central atom. Okay. So the first step we do is we add up the number of valence electrons from the hydrogen and the carbon and the nitrogen. Okay, so you go to the periodic table. Okay, nitrogen is group 5. We got 5 valence electrons. Carbon is group 4. Okay. So 5 and 4 is 9, and hydrogen is group 1, so we've got 10 valence electrons to work with. And valence electrons, or 5 pairs. Okay. Now we can write hydrogen, and then followed by carbon, a bond with nitrogen. Okay, so that's our beginning, because we have two of them bonded centrons, so we can very quickly put them on the atoms that are bonded central atom. Okay, and that takes care of 2 pairs. So what I got left to work with is 3 pairs left over. You gotta keep track of it because you can't lose track of how many pairs you have to begin with, because at the end, you're gonna have the same number of pairs that you calculated. So I got 3 pairs. Now I can't put it on hydrogen because the hydrogen has 2 around it already, so it's happy. Okay, so the 3 can go anywhere you want. I can put them on carbon, or I can put them on nitrogen, or mix and match. Makes no difference. What I prefer to do is to put them on the outside atom and then work my way in. Okay. Now, in doing that, I don't know how I can do that with my mouse, my pen not working here, but I'm going to attempt. Okay, so I got hydrogen bonded with carbon, and then I'm going to put, that's nitrogen. I got 3 pairs, and I'm going to very quickly just assume that I put them around the nitrogen, so that these 2 dots represent the 3 pair on the nitrogen. Okay, hopefully you can envision that. Normally, like I say, in my little pen, I can draw that out. So I got carbon, hydrogen, carbon, and then nitrogen, and then the 3 pair around it. I still have 5 pairs. 1, 2, 3, for 5 pair, right? There's a total of 3 pair on the nitrogen and another pair bonded with carbon. So nitrogen is happy, okay, because it is octets fulfilled. Hydrogen's okay because it needs just 2, but carbon only has a total of 4 electrons around it. And so what you do is you take the one of the pair and share it with carbon. So take one of the pair on the nitrogen and share it with carbon. So when I do that, I should have a structure that looks like this. Like that, and equal. I still have nitrogen and I still now have 2 pair, okay? And so nitrogen is still happy with the lone pair on it and the 2 bonded pair. It's a double bond, right? But carbon only has a total of 6 electrons around it, so it's not doing okay. So what you do one more time. Remember, you can start with single bonds. If that doesn't work, obviously you start with single bonds. To make an octet fulfilled, you create a double bond, which means sharing a pair with another element. In this case, we're sharing a pair with carbon nitrogen to create the double bond. So I'm going to take the last lone pair on nitrogen and create a triple bond between the carbon and nitrogen. The result is that I get a structure that looks like that, okay? Now, check that structure I just showed you there. Does it still have 5 pair? You remember, that's it. You gotta have 5 pair, you can add more or less. So yes, there's 5 pair. On nitrogen, the octet is fulfilled. There's 1 lone pair on the nitrogen and 3 bonded pair and shared with the carbon. So there's a total of 8 around nitrogen. Now look at the carbon by itself. Don't worry about what's bonded to it. It has 3 pair that are shared with the nitrogen, so that's 6. And it has 1 pair that is shared with the hydrogen. And so it's good. So see, this 6 electrons are being shared between the carbon and the nitrogen and count for each one. And this one here is being shared between the carbon and the hydrogen. And that too can count toward the carbon and also counts toward the hydrogen. So carbon now has an octet, nitrogen has an octet, and hydrogen has its duet. So everybody's happy, okay? Everybody's stable. So we get a triple bond. With that information, the next step is to figure out a general formula, which would be the central atom, which is carbon, and we got A, B, 2. 2 and then 3, okay? The 2 represents, B2 represents the hydrogen and the nitrogen. Now you may ask, well, there's a lone pair. Remember, E is only for the lone pairs of the central atom. Carbon does not have any lone pairs, unbonded pair. They're all bonded by triple bond and a single bond. So there's no E here. Okay, we're not concerned about the lone pairs on the bonded elements. So with that general formula, now you go to the shapes table and you look for AB2, which is the first entry. So you can see here how hydrogen could be represented by this atom and nitrogen represented by this atom, and carbon's in the middle. And that bond angle there is 180 degrees, the bond angle between the nitrogen and the hydrogen, 180 degrees. And that is called linear, and there's the bond angle, okay? All right. Okay, now, same process for the next one. You got carbon, a hydrogen, and the fluorine. So carbon brings in 4 valence electrons, right? It's in group 4. Hydrogen brings in one valence electron, and the 3 fluorides, each one is in group 7, right? Group 7, is that a correct statement? Is fluorine a group 7 element? Yes, it is.
Yes.
Yeah, it's good. So 7 times 3, that equals 21. Okay. Now we tally it up, and the whole thing adds
And really,
up.
I'm sorry to cut you off really quick. So it's
Sure.
7 because it's 7 of them, but it's 3 of them with the subscript 3. So that's why we're doing it 7
Mhm.
times 3. Okay.
7 times 3. 7 times whatever number of fluorines you have. Okay. Which at the max you'll be 4 in most compounds. So that's the total of 21. So that whole thing adds up to 26 valence electrons. Okay, I'm just going to call them VEs. VEs, valence electrons, or 13 pair. Okay, every number you should add up. All the valence electrons should tally up to a number that's divisible by 2. Okay. All right. So now, with 13 pair to work with, you're given the central atom, which is carbon. All right. And so you can very quickly, and it's going to be tough for me to draw this in this manner, but obviously, like we did before, we got carbon, and then bonded to chlorine. And then we have that bonded to fluorine, but I can't do all 3 of them here. So if you can imagine those 3 fluorides bonded to the carbon atom in the central, okay? Good. Let's do it. Imagine that's bonded right there. I don't have a line. Imagine that is bonded right there. Okay, and there's a little line between them. So carbon has 4 bonds around it. 3 fluorides, 1 hydrogen. Okay. And what that does now is that takes care of 4 pairs. So 13 minus 4 gives me what do I have left over to work with? 9 pair, right? All right. So think about this for a second. I have 9 pair of electrons to work with. Hydrogen is happy. It's got the 1 in there, okay? If you count the number of bonds around carbon, the way it's situated, it has 8. So carbon is good. But what's happening here, the fluorides only have 1 bonded. Each one is only 1 bonded to the carbon. So it's missing 6. So what we got to do is to place those 6 electrons, 9 pair around the fluoride. So you just tap a line around each fluoride, 3 of them. That gives you 8, and go all the way around. You should end up with a structure that looks like as follows. You see that 9 pair that we just finished calculating? Because they can't go on a carbon anymore, because carbon's happy, it's full. So the only place they can go has to be around the other atoms, the fluorides. Okay. Now count the pair around that structure we just created. You'll see that there are a total of 13. We got 9 of them around the fluorides and 4 that are bonded to the carbon, the central atom. That's a total of 13 valence electrons. Okay. So this is where you got to do an inventory of the electrons when you're done, because whatever you calculate, and if your calculation is correct, then that's what you have to use. Okay, we can't magically just, you end up with 2 extra ones, you just throw them away and ignore them. Okay. Okay, so that takes care of that. Now we generate the general formula, and we have again A, and in this case we got B obviously, but subscript 4. okay? Can be the same or different. Here we got 3 fluorides and 1 hydrogen, makes no difference. It just states that in the central atom, there are 4 items bonded to it. So the general formula is A, B subscript 4. That information, then you take to the shapes table and you look for AB4. And lo and behold, it's the one we were talking about. There's AB4. And there's the 3-dimensional geometry, and we call that tetrahedral, okay? And that angle, that bond angle between the fluorides and the hydrogen are at 109.5. Okay? Now you may ask, why is it that we need to know this? Well, down the road, when we're trying to predict some of the properties of molecules, one way to predict things, whether is it soluble in water, would it have polar qualities or non-polar qualities? To answer that question, we have to come up with the structure first here, because we're gonna, once we know the structure, we're gonna give you more information. And from the structure that we just determined, it will tell you whether that molecule is polar or non-polar, okay? Polar or non-polar, a lot more on that later on down the road. So see how this is tied in. Okay, carbon dioxide. Same thing. Carbon, carbon brings in 4 electrons, 4 valence electrons, okay? So carbon, 4 valence electrons, oxygen, okay? Oxygen is in group 6, and there's 2 of them. Okay, so that tells us that we have a total of 12, is that correct? 12 valence electrons for the oxygen, being it's in group 6. There's 2 of them, okay, 12. So we have a total of 16, correct? And 16 valence electrons for 8 pair. Okay, does my numbers look reasonable? Or do they look correct?
Yep.
Okay, we're given that carbon's a central atom. Okay, so I'm going to draw, I got the oxygen, I just draw 1 single bond. Then I got carbon, draw a single bond, and that represents oxygen. Okay, so that takes care of 8 minus 2. Okay, equals, now I got 6 pair left over to work with. Now, where you put them makes no difference. You can put them anywhere you want. Okay, and you can put them, just put them all the way around until everybody's happy. I tend to want to stick to the outside elements and give it all to them and then work from there. So if I start on the left side of the oxygen, I could put 3 there around it. And then on the right side, I can put 3 around there. Okay. And that takes care of the 6. So I would have that structure I just drew there. But if you can imagine on the oxygen, I got 3 lines on the left side. I got 3 pair on the oxygen and 3 pair on the right oxygen. Okay. The oxygens now are happy. I mean, they would look very close to, if you can imagine that fluoride here, the way I drew it with 3 pair around it and 1 single bond to the carbon, very similar to that. Okay. But carbon ends up with 2 electrons, 2 pairs, and only 4. So here we have an example like we did the first one where carbon is shy, but who they're bonded to has extra they can share. So we're going to take 2 pair, 1 from each oxygen, and create a double bond between the oxygen and the carbon. Okay. When that happens, you end up with the following structure. And so if you look at this, you still have a total of 12 pair. From the beginning, you got 4 lone pairs on the oxygen and 4 bonded pair on the carbon. That's a total of 8 pair, which is what we calculated to begin with and what we got to work with. We had to create double bonds between the carbon and the oxygen because we needed to make sure that everybody had the octet fulfilled. The general formula here, we'll come back to this, is very similar to HCN. We have A, B, and 2. Okay, A is carbon, 2 oxygens. We go to the Schaef's table. Okay, AB2, the first entry. So that's the geometry, which is linear. And bond angle 180 degrees. All right. Okay. Now, with this information, we're going to learn about polar bonds and so forth, but because of the geometry of let me put it through this way, because of the geometry of carbon dioxide, we would anticipate, before knowing that the geometry of carbon dioxide based on the bond, the type of bond, we would anticipate that carbon dioxide would be polar and therefore water soluble. It turns out that's not the case, actually, that because of the geometry, even though they have polar characteristics within the molecule, the geometry puts it in position such that it gives it overall non-polar characteristics. Okay, and that's the kicker, that within the molecule you can have polar characteristics within one bond or 2 bonds, but because of the geometry, totally changes the properties and makes it more non-polar. So knowing the structure helps us determine that, what kind of characteristics it has with respect to physical properties. All right, and finally, the last one here, which would be nitrogen. Okay, here's nitrogen. Nitrogen is in group 5, so it brings 5 valence electrons. Hydrogen, we all know, group 1. Okay, but there are 3 of them, so 3 times 1, obviously. 3 times 1, obviously, and I write it like that to demonstrate what's in parentheses is the number of valence electrons. It sounds like redundant, but I want to make sure everybody understands where I'm at. So we have a total of 8 valence electrons, E's, or 4 pair. Okay, sound like I'm playing poker here, right? Got 4 pair. All right. Now, nitrogen is the central atom, and hydrogens are bonded around it. So if you can envision, you put nitrogen down and then just put in the 3 hydrogens around it, that takes care of 3 of the pair. Now you got 1 pair left. Well, you can't put them on the hydrogens because hydrogens are happy. Hydrogens only in a duet. So it must go on the central atom. It must go on the central atom. And when that happens, you end up with this particular structure. This, by the way, is called ammonia. This is the structure of ammonia. Now, its general formula would be A, B3, and guess what? We have an E. We have an E in the central atom. Okay? A lone pair. So now we go to the Schaef's table, look for AB3E, E, and there's no subscript E because it's just 1, okay? They're for AB3E, and it's sitting right here. So you can envision the molecular geometry as follows. You got ammonia in the center, and then the 3 hydrogens bonded around it. And then on the nitrogen itself, you have a lone pair, resulting in those hydrogen bond, the nitrogen hydrogen bond to be kind of pushed down a little bit. Its bond angle is less than 109, and it has their own special name, trigonopyramid. Yeah. Very polar species, like I stated earlier, we get a lone pair on the central atom, unless for some reason somewhere else in the structures things get canceled out, you end up with a polar species. So ammonia is very polar. Okay, so typical examples given right there. So you should be able to, given the formula, you know, being told who is the central atom. Hopefully you should be able to come up with a structure like we got. So we come up to revamp, and let me rehash here just before we leave this, is we take the formula, determine how many valence electrons each atom brings into the structure, okay, tally it up. You should end up with a number divisible by 2. I divide by 2 to give me the number of pairs. I get the central atom, draw that, and then draw whatever else is bonded to that with what I'm given. And then whatever pairs are left over, I put them around the structure such that I can put them in the manner that you get the octet fulfilled. Remember, hydrogen has a duet. I cannot add more than a pair of electrons onto hydrogen. Hydrogen will always have one single bond. And then I keep adding these electrons until everybody's happy if they got the octet. If nobody has the octet, that means you're probably going to borrow from Peter to share with Paul, so to speak, okay? And you start creating double bonds. If that doesn't work, you got to do one more, do triple bonds. But at the end, you should come up with a structure in which all the atoms have the octet fulfilled, okay? And then from that information, create a general formula, ABE, where A is the central atom, B is what is bonded around the central atom, and E is the number of lone pair, non-bonding pair to the central atom. Once you get determine the general formula, take that information, go to the shapes table, go down the column, find the structure that gives you the geometry and the name of the geometry and the specific bond angle, okay? And these are for chemical compounds that are, we call neutral, okay? Because the next example you're gonna do is we're gonna be using chemical compounds that are not neutral. They have a charge on them, okay? And these are specifically what we call polyatomic ions. Now, where do I get this? Where can I get this information? Well, guess what? Let me refer you back to the periodic table. And if you look at the periodic table, down in the bottom left side, you will see a table. Let me highlight it right here, which is called most common polyatomic ions, okay? These are chemical compounds, specifically anions or cations. We had talked about, the atoms, single atoms creating anions and cations, ions, okay? But we also have examples of what are called polyatomic ions. That is, there's more than one atom, different, and they're bonded just like any structure is, but overall, they have a specific charge, either a negative anion charge or a positive. The most common positive charge ion you were going to work with is this one called ammonia, which, by the way, they each have their own specific name. The name doesn't get changed, okay? That's the name for that structure. Notice it has a positive charge. it will combine with any of these anions that are negative, as long as you got enough of these ions to cancel each other out. So this ammonia can combine with nitrate. We got this guy right here, all right, or nitrite, et cetera, et cetera. So you're already building up your database of chemical compounds that you can produce. And those are legitimate: ammonium acetate, ammonium hydroxide, ammonium cyanide, so on and so forth. Okay. Baking soda, here's the structure for, the bicarbonate ion. Baking soda, the old-fashioned baking soda. Normally it's sodium or maybe even potassium bicarbonate. Okay, now we're going to take these ions and we're going to determine the structure of these. Now there's an added twist to it. Because of the charge, we're going to add a number or subtract a number to the ion depending on the type of charge. It doesn't mean we're adding the electrons or subtracting electrons. It means because these are ions, sometimes the electrons it has are tied up, resulting in a positive charge. Or the other end of the spectrum, the anion, the negative charge, the atom, the structure is such that the electron is on a how can I put this? It's still there, but it's not bonded, resulting in a negative overall charge. Okay. Okay, so let's try some of those. And the process is, like it stated, the same. Okay. Oh, sorry about that. We did talk about HCN. This is just a kind of a rehash of the first example where we ended up with 5 pair of electrons, checked the octet, we took care of 2 of them, and then we created what was left. We put them around the nitrogen. So, but then we checked the octet. We saw that carbon is needing more, so it's sharing from the nitrogen and to create that structure. Okay. All right, so let's talk about the Lewis-Dot structures for polyatomic ions. There's only two changes here. We first have to determine what's positive or negative. Now, the last thing is, when we draw the structure, we actually put a bracket around the structure we come up with, and then we put the charge for the polyatomic ion on the upper right corner. So let's do some examples. We do the same steps, but if it's a negative charge, we need to add more electrons. Okay, it's really more the counting of electrons are there, but we got to count for them. If it's negative, we got to add. And the number we add depends on the charge. If it's just a -1, we just add 1. It's a -2, add 2, etc. Okay. If it's positive, like the ammonium ion, okay, we need to subtract a number from the valence electrons and calculate. Okay. Negative is kind of counterintuitive, right? Negative charge, we add. Positive charge, we subtract. Okay. Now, if you inadvertently, said negative and you subtracted, it's okay. Well, you're going to find out that when you finally get to the point where you start putting things together, you're not going to have enough electrons, even by sharing with anybody else, to even be able to share. So that's a flag to tell you, maybe I inverted what I'm supposed to do. On the other end, if you added electrons, let's say you got a positive charge ion, and you added numbers, when you start putting the structure together, guess what? You end up with extra electrons. And there's no way you can put them anywhere because everybody's octet is full. So that's a flag to tell you, oops, maybe I did it wrong, okay? So think about this. If it's negative and you subtract it, okay, you might be short. If it's positive ion and you add it, you're gonna have way too many, okay? Electrons. So those are flags to tell you which one. All right, and then at the end, we put a bracket around the whole structure, and we end up with you put a charge in the upper right corner. Let's try, for example, the cation ammonium. What we just showed you earlier is NH4 and has a positive charge. Okay, So what we do is we got nitrogens at group 5. So it's 5 valence electrons. We have 4 hydrogens. Each one brings 1. Okay, so a total of 4. Okay. And notice if you forgot, wait, I'll come back for a second. Since it's positive, we subtract 1. So we have 8 valence electrons or 4 pair. Now let's think about this for a moment. What if you inadvertently forgot to subtract this step and you forgot where'd it go? And you forgot to do this? Okay, let's say you forgot to subtract it. Well, you end up with 9. There's a flag right there, 9. Remember I told you everything is always divisible by 2, whatever number you come up with. So that's a flag that maybe you forgot a step. All right. So let's say you added, instead of subtracting, you added 1. So now you end up with 10. And guess what? You end up with 5 pair. Okay, go that route. Well, when you end up with the structure, you're going to see that I got 5 pair. And I got 4 of them taken care of, but I got that 1 pair I can't put any place. I can't put them on hydrogens. I can't put them on the nitrogens because nitrogen is going to be happy. It's already full. So that's a flag, again, to tell you something went amok and you have to go check your accounting, all right? You should end up with this because nitrogen is the central atom. There's 4 hydrogens, so I can very quickly draw 4 items here. 4 lines to represent the hydrogens, okay? And that takes care of my 4 pair. And I'm done. Check the octet for nitrogen, it's happy. Check the duet for hydrogen, all is happy. And then I draw the bracket in the plus on the upper right corner. Don't forget that, the bracket in the upper right corner, that is the configuration, the format for writing electron structures of polyatomic ions. As I stated, let's say you added and ended up with 10 valence electrons, that's 5. If you look at the structure shown there on the right, if I end up with 5 pair, I can't put it on anywhere. You know, if I were to say, well, I just put it in the central atom. Well, think about that. Let's say you put it right there. Here's a line. Well, you know, that's 10 electrons on nitrogen. Right? 4 of them are bonded and the 1 on there, 1 lone pair. Well, that's 10 electrons. That's a violation of the octet rule. So that wouldn't function. Okay? So that right there tells you is a flag to tell you something went amok. And if you forget that step, if you forget to subtract 1, you end up with 9, which is not divisible by 2. Okay? All right. And this is the ammonium ion. So again, rehash, same process, add up the valence electrons, and then if it's positive, you subtract, okay? And then you'll be told, it's unfortunate the nitrogen's not underlined, but you'll be told who's the central atom. Always, you'll know that. All right, let's do a couple of these. Some of these, not to worry about what they are, but we'll get to those in due time. So we got BrO3. It is a negative charge. Okay, it's an ion. So the steps are the same. In fact, all of these 3 have a negative charge. Okay, so that means in the case of the positive, we subtract it. The negative, we're going to add. All right, so we have 1 bromine that brings 7 valence electrons. Notice I said bromine because in this case, bromine is the central atom. So it's not bromide. It's bromide when it's not the central atom. We got 3 oxygens, which bring in 18 valence electrons. And we have to add 1 electron. So we get a total of 26 valence electrons. Let me back up for a second. When we got here, I forgot a step. The last step is general formula. Same process as we've done before. It's A, nitrogen's A. Guess what? B, we got 4. Okay, 4 four atoms bonded around the central atom. So then we take that general formula, AB4, and guess what? Go through your trusty shapes table. You will soon pick up on
Tetrahedral.
tetrahedral, exactly. Thank you very much. Because you'll soon pick up a trend here. Now, even though there's totally different compounds, they're going to share geometry. And with that, AB4 is for that ammonium ion shares the geometry of the CH4. It's tetrahedral. Okay. All right, good. So we go back here. So we were at bromine, 1, 7, and 18 for the oxygens, and we add one electron because it's a negative ion. Okay, and that gives us a total of 13 pairs to work with. So we got bromine in the middle, and then we can very quickly bond the 3 hydrogens around. Okay, but then we have a lot of electrons left over. Okay, so if we got 13 pair and I take care of 3 because it's bonded, that leaves 10. So I go to the outside. That's where I prefer to start, and I fill up the octet for each oxygen, and that takes care of 9 of that pair. Okay, which leaves me 1 pair to work with. Well, the only obvious place it can be is in the central atom. Okay, no different than we've been doing. Now, if you count all the pairs of electrons there, guess what? You have 13. You have 9 lone pair around the oxygen, 3 oxygens. You have 3 bonded with the bromine and the oxygen, and 1 lone pair. That's 13 valence electrons. Okay. General formula. Anybody want to take a shot at that? What do you guys think the general formula for this guy would be? Obviously, it's going to be A. What about B?
B3.
B3. Okay, that's good. Then we have E. You got it.
2. Or just E. I forgot when it's 2. You don't say the rest.
You got it. Exactly. So it's AB subscript 3 E. E is the lone pair. From that information, we go to the shapes table. ABE3. Oh, here. And there we go right there. Very similar to the ammonia, the NH3 we did earlier. Okay, but like I said, even if it's a polyatomic ion or a neutral compound like ammonia, they're going to share the same type of geometry. We can determine that. So it's trigonopyramid, has a bond angle less than 109.5. Okay. All right, let me finish this slide up and then we'll call it a day. Here we got SO4. In fact, this is called the sulfate. Next time you eat something, look at the label. You're eating a lot of sulfates. Sulfates. Right, there's a structure. Sulfur's the middle central atom. We got 6 valence electrons coming from sulfur, I should say. We have 4 oxygens, a total of 24 valence electrons. And then we have add 2, see, I made a mistake myself. Add 2 because that's a -2 charge. So that gives us a grand total of 32 valence electrons or 16 pair. All right. Sulfur is the central atom and the 4 oxygens are bonded around it. So I can very quickly take the sulfur and then bond 4 oxygens around it. That takes care of 4 pair. And that leaves me with 12. 16 minus 4 leaves me with 12. And I can't put any more on the sulfur. So the only place they go will be around the oxygens. And you end up with the following structure. Oh, right there. See without stating it, I got sulfur, central atom, 4 oxygens. I can very quickly bond them there. And then I'm left with the remaining oxygens that I can't put any more in the sulfur. Obviously, the only place they can go is on the oxygen. So I put them around there. check your valence electrons. There still should be 16 valence electrons there. There is. And then our formula, any idea what this general formula would be? Who would like to give that?
AB4.
You got it. AB4A represents sulfur, and the 4 represents the oxygen. So from that, like we did before, we go to AB4, which is right there. There's a geometry given to you. Its name is tetrahedral, and its bond angle is 109.5. Okay. All right, so far so good. And finally, the last one here, same scenario. Carbon brings in 4, nitrogen brings in 5, and we've got a negative charge, so we have to put in one more, total 10. Okay, this is very similar to the HCN we did earlier, except it's got a negative charge. The hydrogen has been removed. You see? And then you have 5 pair, and same scenario, go around there. You're going to end up by having to make triple bonds, just like we did the first one. Then each one has a lone pair. Now, when you have 2 atoms bonded together, and that's it, they're really, technically, there isn't a central atom. It's just two atoms. And so structurally, it's a straightforward AB2. Well, linear, not even AB2, just linear. You got 2 species, so it's just linear. Okay. All right. So, tell you what, let's stop it here. We'll continue on Thursday, and we'll continue about the next step, which is basically what I've just been talking about. Like I stated before, I always try to give you a taste of what's coming. It's the same thing, real fancy name called the valence shell electron pair repulsion. That's a mouthful, right? Or VSEPR. What that means is this: we got lone pairs in the central atom. They take up space because they're repelling each other. And what results in that? Well, that results in the rest of the molecule being kind of deflected, or the bond angle gets smaller. Okay, that's all it's talking about. Okay, so let us stop it here.